Lab 1. Charge tapes, measuring the amount of charge on an ordinary object. In this lab, I generated and determined the excess charge in clear tape. I then created a simplified computer model of the situation to be able to calculate the charge of each piece of tape along with some other parameters. The resulting charge was 4.18 times 10 to the negative 8 coulombs. Charge was generated in the tape by layering two pieces of clear tape one on top of the other and then by quickly removing the top piece of tape. Two charged pieces of tape created this way are assumed to have the same charge, and therefore will repel each other. Note that it is important to handle the tapes as little as possible, as when handled, the tapes can discharge, thereby losing their charge and their properties. The repulsive force generated by the two pieces of tape with the same charge can be used to float one piece of tape above another piece of tape. The tape floats in a constant position when the electric force applied to it by the tape below it is equal to the gravitational force pulling down on it. The magnitude of the gravitational force can easily be calculated using the mass of the tape, allowing the electric force to therefore be calculated using it. It is important to discuss the specific physics principles in play here. The first important principle is Newton's second law. Net force is equal to mass times acceleration. As the levitated tape is stationary, it can be concluded that it is experiencing no acceleration. If acceleration is zero, by this equation F net equals ma, the net force must be equal to zero. As the only two forces acting on levitated tape are gravity and the electric force applied by the other tape, the force of gravity in magnitude is equal to the magnitude of the electric force. As gravity is downwards, the electric force must be directed upwards in order for the forces to cancel out and produce zero acceleration. Secondly, electric force can be calculated with the equation on the screen. With a known magnitude of force, which we have due to Newton's second law, and a known separation, which we have measured, and with the assumption we made that the charges are equal between the first tape and the tape being levitated, the magnitude of the charge itself can be calculated. The sign of the charge is determined using a plastic pen with a known negative charge, and observing how the tape behaves around it. As the tape is attracted to this pen with a known negative charge, the tape must have a positive charge. This is known by the basic principle that things with like charges repel each other and opposite charges attract. In this staged replication of the experiment, you can see the method used to measure the separation between the tapes in a steady state. Note that the measurement was fairly imprecise due to the fact that the ruler had to be fairly far away from the actual site of the experiment, as the tape was attracted to the metal ruler. Here is the output of the code used to model the situation and calculate the charge. It calculates a charge of 4.17612 times 10 to the negative 8th coulombs, a force of gravity of 9.81 times 10 to the negative 3 newtons, an electrical force of positive 9.81 times 10 to the negative 3 newtons, an electron deficit on the levitated tape of 2.6 times 10 to the 11th electrons, and an average electron deficit per atom on the surface of the levitated tape of 1.37 times 10 to the negative 7th electrons per atom. Here is the code used to generate that model. Firstly, constants were set up, such as the known value of 4 pi epsilon naught, the charge of a single electron, a scaling factor used to make the model more readable, the known value for g, the known value for the length of tape, the known value for the width of the tape, the known linear mass of the tape of 1 gram per meter, which then allowed the calculation of our piece of tape, which was 1 meter long, therefore giving it a mass of 1 gram, the separation between the two tapes of 40 millimeters, and the approximate length of one atom of 1 times 10 to the negative 10 meters. Then, the operations described earlier could now be performed. First, the magnitude of the force due to gravity was calculated. Then, by rearranging the equation for the electric force to solve for the magnitude of the charge could be computed using the force due to gravity. Finally, the electric force could be recalculated as a vector, and the gravitational force could also be recalculated as a vector by multiplying it by its known direction. This would allow us to model the two electrons and the arrows pointing up and down with the correct magnitudes. The electron deficit could then be calculated by simply dividing our calculated charge by the charge of a single electron, thereby giving us the number of electrons missing. Finally, by dividing the electron deficit by the number of atoms on the surface of the tape, we could calculate the electron deficit per atom on the surface of the tape, or rather an average value. The number of atoms could be calculated by taking that length of a single atom, using that to estimate the area of a single atom, assuming that atoms are square, and then dividing the total area of the tape by the area of a single atom, thereby giving us the number of atoms on the surface. A link to the code is available in the video description. Returning to the original model, you can now see the two particles representing the two charges, with the downwards orange arrow representing the force due to gravity on the upper tape, and the upwards blue arrow representing the electric force applied by the lower tape onto the upper tape. Some additional questions posed in the lab were what would occur if electrons had a positive charge and protons had a negative charge. In this case, the situation would play out exactly the same, merely with reverse charges, as the oppositely charged tapes would now merely be negatively charged, as they would be lacking positively charged electrons and would therefore still repel each other.